A heating curve explains the relationship between the amount of heat energy absorbed by a sample of a pure substance versus the change in temperature or the change in phase experienced by that pure substance. Hi, Mr. B here. In this video, I will explain how to draw a typical heating curve for a sample of H2O. As ice absorbs heat energy over time, two transitions will occur. First, the ice will melt. Secondly, the melted ice, or liquid water, will vaporize. This illustration represents a typical heating curve for H2O, where the ice is represented by line segment AB. And according to the information, we're beginning with ice or solid H2O at a temperature of negative 25 degrees Celsius. As the sample absorbs heat energy, the temperature of the ice will increase until the melting point is reached. For H2O, the melting point at 1 atmosphere of pressure will be 0 degrees Celsius. Notice at this point, the line will flatten into a plateau. This indicates that during this time period where the sample is continually absorbing heat energy, the temperature is remaining the same. Another name for temperature is average kinetic energy, where kinetic energy represents the energy of motion. So on a heating curve at the plateau, the average kinetic energy or the temperature does not change. After a certain amount of heat energy has been absorbed, the temperature of the sample will begin to increase again. This area represents the liquid part, the liquid phase of H2O that we commonly call water. Once again, the temperature will increase until it reaches the point where another phase change will occur. This time, the phase change will be a transitioning from the liquid phase to the vapor phase. Notice that during line segment DE, the temperature or average kinetic energy remains the same. A key point to remember about a heating or a cooling curve is that at the plateaus, the temperature or the average kinetic energy remains the same. The sample will absorb heat energy until all the liquid has been vaporized. At this point, the temperature may increase again. This state of matter represents the gas or vapor phase. Now let's calculate the energies involved during each line segment of the heating curve. But before we begin to explain the energies involved, we must first identify the formulas that must be used. During line segment AB, the formula will be Q is equal to MC delta T, where Q represents the heat or enthalpy, M represents the mass, C represents the specific heat capacity, in this case the solid phase or the specific heat capacity of ice, and delta T represents the change in temperature. Line segment BC, Q is equal to M H sub F, where once again M represents the mass and H sub F represents the heat of fusion. Line segment CD, notice during line segment CD, as with AB, the temperature is changing. So the formula to use will be Q is equal to MC delta T. Now that brings us to line segment DE, where our sample will now be vaporized. Notice that the line segment is a plateau, so there is no change in temperature involved. Q is equal to MH sub V, where H sub V represents the heat of vaporization. Line segment EF, Q is equal to MC, temperature change, write in the delta T. Okay, so these are the formulas required to calculate the total amount of heat energy absorbed during a specific process. Each formula in the calculation will require a constant. The value for the heat of fusion is equal to 334 joules per gram. The value of heat of vaporization is equal to 2260 joules per gram. Of course, where gram is equal to the grams of H2O. The specific heat capacity of water, 4.18 joule per gram times degree C. In this case, a temperature unit is required because during this process, remember, on a heating curve, the temperature is increasing. In terms of the ice, the specific heat capacity of ice is half of the specific heat capacity of water, 2.09 joule per gram degree C. Remember, once again, that the temperature of ice may increase until the melting point is reached. In the case of water, that melting point will be 0 degrees Celsius. And of course, the heat capacity of vapor is 1.84 joule per gram times degree C. Now let's apply what we've learned so far to an actual practice problem. Consider the following. How many joules of heat energy are required to completely vaporize 25 grams of ice that has an initial temperature of a negative 25 degrees Celsius? On the heating curve, we are beginning at point A, and we wish to go to point E. So the first step in the process is to use the enthalpy of ice formula, where enthalpy or heat is equal to MC delta T, where in this case the specific heat capacity of ice is equal to 2.09 joule per gram times degree Celsius. So Q is equal to 25 grams times 2.09 joule per gram times degree Celsius times a delta T of 25 degrees. This now takes us to point B. At point B, the process of melting is occurring. We call this process fusion. Thus, the term heat of fusion. The heat of fusion of ice is equal to 334 joule per gram of ice. Since we're given 25 grams, Q is equal to 25 grams times 334 joules per gram. This now takes us to point C, and we wish to get to point D. This is basically the calorimetry formula. Q is equal to mc delta T, where m is equal to 25 grams, C is equal to the specific heat capacity of water, and delta T is 100 degrees C. Now we're at point D. To get from point D to point E, we use this enthalpy formula, where now the constant is heat of vaporization. 25 grams times 2260 joule per gram, which now takes us to point E. And if we needed to go to point F, we would use this formula, where now Q is equal to 25 grams times 1.84 J per gram times degree C, where in this case now, let's say we wish to heat our steam to 125 degrees, so now the temperature change is 25 degrees C. Now simply perform the calculations. 25 grams times 2.09 joule per gram degree C times 25 degrees C is equal to 1,306.3 joules. So the amount of heat energy absorbed during the warming process of the ice will equal 1,306.3 joules. How much heat energy is required to melt the ice? 25 grams times 334 joule per gram is equal to 8,350 joules, which now brings us to point C, where we're now raising the temperature of the water sample to the boiling point. 25 grams times 4.18 joule per gram times degree C times 100 degrees C is equal to 10,450 joules. At this point, we're at point D, and we want to go to point E, so we want to vaporize the water sample. 25 grams times 2260 joule per gram is equal to 56,500 joules. And of course, if we now wanted to heat the steam or vapor, 25 grams times 1.84 joule per gram degree C times 25 degrees C, which is the max temperature on the y-axis, will equal 1,150 joules. To determine the total amount of heat energy required for the entire process, simply add the values of Q. 1,306.3 plus 8,350 plus 10,450 plus 56,500 plus 1,150 So the total amount of heat energy required for this process is equal to 77,756.3 joules, which may be also written as 77.8 kilojoules.
Goodbye.